everyone for coming, and before I introduce Wendy, I'd like to say the next talk that we're sponsoring is going to be May 1st. It's Alfonso Karamazza, Representations of Mind. Wait, sorry, I'm forgetting his title, unfortunately, but it's a talk in the Neurophilosophy series, and it will be, I think it's Representations of, Levels of Representation in the Mind-Brain. So, I'm getting the title confused. So that will be May 1st, and today it's a pleasure to introduce Wendy Parker. So Wendy is a very good personal friend. We go back to the days of graduate school. She finished her PhD from the HPS Department, History and Philosophy of Science Department in Pittsburgh in 2003. The same year I finished mine, although I'm not going to tell you who started first. Since then, she's been at the Ohio University, and very recently has accepted a position at the University of Durham. And she'll be one of the people starting the Center for Humanities Engaging Science and Society. You notice there's a really nice tagline in the middle of that. And so they'll actually be working on projects that are similar to some of the things that we're pursuing. So it's really exciting to see that project getting started and seeing that Wendy's going to play a part in it. She's been working for a number of years on a really rich set of topics relating to computer simulations and their epistemic status. How do they compare to experimental knowledge and other ways of deriving knowledge of systems, and in particular looking at computer simulations in meteorology. And so today she's going to talk to us about moving beyond prediction, the computer's inductive device, and the study of weather and climate. So please join me in welcoming Wendy.
Thanks everyone for coming. It's great to be here. Thank you to the Rotman Institute for inviting me and giving me a chance to tell you about some science that I just really love, and I always feel excited to get to tell other people about it and hopefully get you excited about it as well. Yes, we're going to have a little tour of some history at the beginning, but I'm not going to pretend that it's a historically rigorous kind of talk here, but it'll figure it here and there into the story I want to tell. So let's talk a little bit about before the computer came along in atmospheric science and climate science. Already by the early 1900s, scientists had identified a set of differential equations that they thought, in principle, they could use to forecast the weather. And the sort of landmark paper in this regard is a paper by this Norwegian physicist, Wilhelm Bjerknes, in 1904, where he sort of lays out the equations, at least verbally, that he thinks should be solved, and then laments the fact that, of course, we can't solve these equations analytically. And so if we want to try to use them in any way to forecast the weather, we're going to need to use, say, graphical methods, using maps and being creative in that way, or maybe we can use some numerical mathematics by hand and do some calculations, though those methods were still in development and the calculations were onerous. So it wasn't until the 1920s that somebody really took a shot at the numerical approach. So trying to solve a set of thermodynamic and hydrodynamic equations, these PDEs, trying to solve them for a very limited domain for a short time period, and it took a month and a half to do the calculation, and it was wildly unrealistic. And this was by Louis Fry Richardson. It's a wonderful book that he wrote describing his efforts, and a wonderful historical story to tell. But in any case, it sort of was disconcerting and pretty depressing. It didn't look like it was going to do much. So when the digital computer came along, it was sort of like, well, maybe we have more hope. Maybe we have hope that weather prediction using these equations and maybe more could actually happen. And what had to happen along with that was the equations needed to be sort of massaged and simplified in certain ways, filtering out certain motions that were causing problems in Richardson's attempt. But we had a sort of filtered set of equations, and now we had this tool, this calculational tool that might actually be put to service here in applying numerical methods. And so in 1950, there was what we'll call the first forecast, successful weather forecast by using the ENIAC, which you see depicted in the picture over there on the right. And I still put forecasting quotes because it did take 24 hours to make the 24-hour forecast. But when they looked at it, it really, it had promise. It was getting things that looked roughly right for what they were trying to do. And so it was a really exciting thing. And within 5 years, as I indicate here, by 1955, there were operational forecasting centers being set up and starting to be run. So it really took off. And everybody always complains that the weather forecasts, weather predictions are not very good, but in fact they are pretty good, and they've improved steadily since 1955. I'm sorry you probably can't see these graphics here, but this is 1955, this is 2005, and this is just showing the change in score on a certain skill score that's used to track the skill of the forecast of the height of the 500 millibar level, which is a height above the ground that is very important for steering large-scale weather systems. So getting that right is important for getting a lot of the weather forecast right. So what you can see, hopefully, is that at least on this skill score, right, we've seen steady progress. This is for a 36-hour forecast. This is for a 72-hour forecast. So they may not be as good as you'd like them to be, but they are improving. So I think the sort of hope for weather forecast has been realized in a pretty striking and impressive way. People have been able to use the computer for this. But as you notice, the title of my talk today was Beyond Prediction, because while weather prediction is what people often think of when they think about sort of the great contributions that the computer has made in say, weather and climate, it's really another use of the computer that I think is at least as important and really worth discussing, which is its use in advancing understanding. And that's really what I want to talk about today. Before I get into the quote that motivated my title, I just want to say very briefly something about the models that I'm talking about. And I'm not going to show equations. I'm not going to go into any of the details. I don't think it's important for the story I want to tell. But if you're interested, we can talk more later and I can point you to things. But so going from, say, then to now, say from the 1950s to now, what has happened? Well, fundamentally, the approach is the same. We're thinking about discretizing these differential equations, solving them using numerical methods. So we make them discrete, solve them with numerical methods, use the computer to help us with the many calculations that are involved in applying those numerical methods. But what's changed is that, so at first we maybe had subglobal, maybe we had a limited domain or a hemisphere. Now we have global models. And this is meant to be a little schematic to give you some idea of the kinds of models we're talking about. The general idea would be you would have this grid of points, and you would want to solve the set of equations at each point. So at each point, you're going to have some value for temperature, for pressure, for wind speed in 3 different directions. You're also going to need to think about the radiation passing through the atmosphere, whether clouds are forming, whether precipitation is forming, whether there's evaporation coming from the land surface. All of these things need to be taken into account. And so that's what this very, way too small picture is showing you some of the many processes that are going to be involved here. So each one of those is going to be, at least in the lowest grid cell, and then you have these all around the globe. So as time went on, people said, well, we need more than just those original equations that Bjerknes had mentioned, which were really for fluid flow on a sphere with some differential heating. We need to think about radiation and all those other clouds, all the other things I was telling you about. So we started to bring those processes in. And then people wanted to do not just daily weather forecasting, but climate. And for that, you have to, for instance, take into account the ocean, the changes in the ocean, a dynamic ocean. On the time scale of, say, a day or two, the ocean isn't changing that much such that it affects the weather. But if you're talking long term, the ocean is a huge driver of climate. So now we needed models that also had an ocean component, and so on. So that has been happening. And also there have been just massive increases in resolution of these models. So this, you probably can't see this too well, but this is sort of showing the depiction of Western Europe in sort of typical models at the 4 different IPCC assessment reports. So this was in 1990. You can't even really make out that it's Europe. And the 1996, 2001, and then 2007, where we're down to what they call T106 resolution, which is approximately 110 kilometers on a side in the grid box. But you can still think that that's still pretty large, right? Each point is representing 110 kilometers on a side and then some vertical. So the resolution has massively increased, but it's still somewhat coarse. I just want to, before I move on, I just want to say very briefly, I'm going to be talking about both weather and climate models. They tend to have the same kind of dynamical core, which I've talked about at the beginning when I spoke of Bjerknes. Climate models then are coarser in their resolution, and they also bring in some additional processes like the dynamic ocean and so on that are needed. But they're related models. They differ in their resolution and the whole set of processes that they include. But I'm going to be sort of speaking of them interchangeably. So if there's anything about that bothers you, feel free to ask me a question about it as we go on. And just to keep you awake, I have a little simulation, a little output from a simulation. This was from a National Center for Atmospheric Research climate model run at a higher resolution than any of the ones I showed you on the previous little picture there. And what you're seeing in white is just water vapor, and little flashes of orange that you may be seeing are precipitation. This is just for the month of January. Now this is for T170 resolution, which is a pretty high resolution climate model. But if you wanted to do weather forecasting, you'd be even much higher. So a weather forecasting model today might have grid boxes that are, say, 20 kilometers on the side or 30 kilometers. So there's a wide range in the resolution. Okay, just wanted to give you that background so that you had a little better sense of the kinds of models that I'm going to talk about and that I want to suggest are really important for this, for making progress toward understanding the atmosphere and understanding the climate system. So it really was not long before people started saying, the computer is not just good for prediction. This is an extremely valuable tool for us when it comes to understanding the atmosphere. And so I have a quote here from Jewel Charney, who was the scientist who was probably most instrumental in developing that filtered set of equations that was used to make some of these first forecasts. So someone intimately involved, and I'll come back to this at the end, in the start of the development of simulation of the weather. And here's the quote, which I'll revisit again as we go on. He said, "The radical alteration that is taking place in meteorology now is due not merely to the ability of the machine to solve known equations with known initial and boundary conditions, like a prediction problem, but even more to its ability to serve as an inductive device." And so it's that phrasing that inspired the computer as inductive device in my title. Sort of, when I first encountered this quote, I thought, what does he mean by the computer as inductive device? I wasn't sure, and over time I think I have come to have a little better sense of what he has in mind, and I'll be talking about that and maybe going beyond what I think Charney had in mind. So this was already in 1955, just as operational weather forecasting was getting started. So here's what I'm going to do. I've just finished my introduction. What I want to talk about is how the computer is sort of promoting this goal of understanding. I need to say a little bit about what I mean by understanding. If I want that to be the goal here. And then I'm going to talk about 3 ways in which, in this area of study, which I abbreviate the study of weather and climate, that's SWC, because it's too long to type, 3 ways in which the computer has been used, and especially computer simulation, to pursue this goal of understanding. One will be its use in generating surrogate observations. One will be its use in testing hypotheses. And a third will be its use in a practice of sort of being able to experiment on models in particular ways. So I'll talk about each of those in turn and then give some concluding remarks. And I'm sort of viewing this as a bit of a tour. Like I said, I want to sort of point you to some science that maybe you don't encounter in some of the typical history of science classes that you take. And along the way, I'm going to have these little silly flags pop up at a few places where I think that there is a lot more philosophical work to be done, where I hope that people will take up some more action and pursue some more philosophical, pursue some of the questions and issues that I want to flag. Okay, so I'm going to get one right away when it comes to this issue of understanding. The more I thought about it, the more I really didn't know how to characterize understanding. And there's this long history of understanding being a sort of unappealing topic in philosophy of science, that it's best left to the psychologists and we're concerned with explanation and that's all. And that sort of changed in the last decade. People have started to become interested in understanding and take it seriously as a philosophical topic of investigation again. But still, starting from the classic papers and things, I was trying to ask myself, what do they mean when they say we want to understand what's going on here? And so the best I could do was extract what I think are 2 kinds of understanding that they have in mind. One is going to be understanding why a phenomenon or event occurs, where that phenomenon or event is typically characterized, as I say here, in terms of a small set of properties. And I'll give you some examples in a minute. And the second sort of understanding that I think they're going to be pursuing, and that I think the computer is helping them make progress toward, is understanding a complex system or a complex phenomenon. And again, I'm going to go into each of these 2 now in a little more detail. But what I want to flag is that these are different not only in their targets, in what is trying to be understood, but also I'm going to suggest in the next couple slides in what the understanding consists in. They're related, but they are different, I think. Okay, so I want to talk about each of those 2 in turn. So understanding why a phenomenon or event occurs. You might want to understand, for instance, why is there an extratropical jet stream? Why is this narrow region of accelerated air located where it is pretty persistently? You might want to understand why, say, New York City got a record snowfall on a particular day. Why did that happen? You might want to understand why severe storms in the central U.S. sometimes split into two separate storms, a topic that I think is a really interesting scientific topic. So this is just 3 snapshots from a radar image, 3 radar images ordered in time. So here you see a radar signature of a large thunderstorm. A little later, you can see it's starting to break into 2 different red blobs. Those are sort of the most intense areas of the storm. And then here, now you see it's totally separated into 2. And oftentimes the right one persists and grows while the left one dies out. So you might want to explain, why does that happen? You might want to understand, why does that happen? And it turns out that this kind of understanding why a phenomenon or event occurs, I think really what they have in mind there is something like explanation. They want an explanation of that occurrence, and they usually want a causal explanation. And again, when I say they, and I'm speaking in these generalities, I'm giving you my best attempt at extracting from, say, textbooks, monographs, classic papers, what I think they're going on about. They don't say, now we're going to give you our theory of understanding, right? So I think they, usually what they want is a causal explanation, and you will see many references to mechanism. You want the mechanism by which storm splitting occurs, say. Or more generally, I think you can talk about having a causal story. So you might want to talk about how certain conditions and processes and forces acting together manage to produce the thing that you want to explain, or in this case, understand. So this understanding is really very closely synonymous with explanation. The second one, understanding a complex system or phenomenon, this I think they have in mind when they say we want to understand supercell thunderstorms. We want to understand hurricanes. Or we want to understand the atmosphere, or the climate system as a whole, right? Equally often, as you see someone saying they want to understand why why storm splitting occurs, you would clearly see that a central goal of the discipline, right, is we want to understand the atmosphere. We want to understand the climate system. Well, what does that mean? We want to understand these things. And here's my best current attempt at distilling down what I think is what some of the key ingredients. So here we don't have a sort of clear completion point. It's not like you arrive at an explanation and you achieve the understanding that you were seeking. It's something that occurs in degrees, to the extent that you have descriptive knowledge of the structure and dynamics of the thing that you want to understand. So say the supercell thunderstorm. What's its structure like at different time points? How does it evolve dynamically? So even just descriptively, what is it like as it goes on through time? You do want explanations, so you can see there is a connection with that first form of understanding that I was talking about. You want explanations of the salient features and behaviors of the system or phenomenon. Why does it split in 2? Why is the right moving storm favored? Those sorts of things. And this is the one that I'm still not sure how to relate to the others yet, but I think you want something like an ability to synthesize and apply this knowledge, the 2 kinds of knowledge that I've just not mentioned, to accurately answer additional questions. So there's something about being able to use the knowledge that you've acquired to answer additional questions when someone throws them at you. And we might get into a discussion about whether that ability is sort of derivative from that knowledge, part of it, and this is, I think, some of the debate that's going on in the literature on understanding right now. So my flag that I put up could equally well has been put here for more work on this, I think. All right, so these are the 2 notions of understanding I have in mind, and so then the task is how to tell you a little bit about why having the computer and being able to use the computer to solve equations that were not solvable in any meaningful way beforehand, why that would contribute to these kinds of understanding. And the first way is going to be via the generation of what we might call surrogate observation, sort of replacement for more typical direct observations. So these are some of the cool phenomena that meteorologists get to study, right? Things like supercell thunderstorms, so this is just rain, but a big rotating thunderstorm. Tornadoes, which are often associated with these kinds of storms. But you don't really want to get too close to those. You don't want to, I mean, some people do. Some people notoriously thrive on driving right into them, but they're dangerous. It's not easy to collect data about what's going on inside there. So you can point radars, you can try to position yourself, but you're still going to get a fairly limited collection of readings about, say, what the pressure, wind direction, and so on are at a sort of fine structure scale of the storm. So one of the ways that simulation has really played an important role in the study of these kinds of phenomena is by in effect, providing a replacement for those data. Now, of course, we're going to have to struggle with these questions about how seriously to take them and so on. We're going to come back to that. But one of the ways that computers have been important here is that if you run a simulation of a supercell, you have data for every model variable at every grid point in the model, any level you want. You have access to that information in the simulated storm. So you might generate, plots like these. These are for two different cases of convection. The details aren't important. What's important to see is that all of these little dots represent wind barbs, wind vectors. So if you're interested in thinking about what the winds are like inside, at least in the simulated version, you can see what's going on inside the simulated storm. So you find quotes like the one I have on the right here. Simulations provide complete kinematic and thermodynamic data both in and around a storm. And I might have wanted to say a simulated storm, but that's the actual quote from a paper, a review article on these severe weather storms. So you can examine those output, right? You can examine those plots as if they were real data. You can plot them in the same way that you would plot real observational data were you able to collect them. So you can look at how do things happen, what order do they happen in, which things come first. This can actually be really useful information. And here, it's certainly the case that advanced visualization techniques are really important. So learning how to extract the information that is useful for, say, constructing your explanation from the massive simulation output that you produce. I'm going to put a little flag there because I think this is another one of these topics that could really use some more attention, sort of the role of these visualization tools in the shaping of the science. It's not been given much attention. And yet, if you go to a place like the National Center for Atmospheric Research in Boulder, Colorado, you will find a room in the basement of the facility, which is like the visualization lab, where you have these huge screens where people go down and look carefully at the results of their simulations, visualized after a whole lot of work to produce those visualizations. So it is an important part of the practice, but it's not discussed very much. So another little movie to wake you up in case you're getting bored. This is just a snapshot at one point in a simulation, so we're sort of rotating our perspective. This is a simulation of a hurricane using the WRF model. The details aren't important. What you see, if you can see them, are sort of lines representing the flow of air, telling you something about if you were to have a little massless particle, how would it be traveling? And then you're seeing also some information about water vapor, and cloud boundaries. And again, the details are not important. What I want you to see is just to think about how looking at results like that could be of use to you if you were someone who was trying to think about the dynamics of what's going on internally to that storm. So if you're looking at simulation results in this way, right, you might be led to formulate new descriptive hypotheses, like, maybe this is what the structure is like. I might not have thought it before, but maybe this is what it looks like inside that storm. You might be led to formulate new explanatory hypotheses, new causal accounts of how something is produced. Or you might be led to, say, favor an existing descriptive or explanatory hypothesis over a rival. And I'll give you an example of that here. I just want to mention briefly that, and you'll see this come up in the quotes I want to show, but insofar as people do extract explanations from this sort of surrogate simulated data, these are usually treated as how possibly explanations or how plausibly explanations, depending on the particular case at hand. But I'll show you in a second that sometimes they're taken quite seriously. So I'll show you what I mean by that here. I just want to suggest, imagine that you're in effect studying these results as if you were studying data that you had collected observationally, and you're formulating hypotheses in the way that you would have if you were able to get data in more traditional ways. So here's just an example that I encountered in a class I was taking on cloud dynamics, and I found it very striking. And so for a while there was this debate over sort of in what order things happened inside supercell storms, particularly in connection with the formation of tornadoes. And so the question was, does increasing rotation in the storm at a low level come before and causally contribute to the formation of a particular structure known as the rear flank downdraft, which was thought to be somehow connected with the generation of tornadoes? Or is it the other way around? So sort of a causal ordering hypothesis. Does this come first and somehow contribute causally to that? Or is it the other way around? And people could sort of tell themselves stories either way. So one hypothesis would be the rotation comes first, it's causally prior. The second hypothesis would be, no, it's this rear flank downdraft, this particular downward motion of air that comes first. and is somehow causally contributing to the rotation. And what happened was, when people finally were able to do some simulations of these storms, they found that things happened in a particular order in the simulation, and some people took this to be really telling about what's going on. So you find this quote inside a classic text on cloud dynamics. Bob House says, "This dispute about the ordering appears to have been resolved by modeling studies which show that the increased rotation at low levels produces a minimum pressure at the ground, which then induces the rear flank downdraft." So, there's a sort of appeal to what was observed in the simulations as a way of resolving, or at least favoring, one of those two hypotheses over the other. He sounds more optimistic in here than some other writers. I'll show you another quote now. So this is another quote from a slightly later 2002 review article, right? So it starts out really positive, right? It says, "Significant advances in our understanding of supercells no doubt have been made by numerical models. It's probable that some conclusions drawn from simulation results never could have been made from observations or theory alone." There's a lot of credit given, but then you get the however. However, the author shares the view expressed by Chuck Doswell. "The rear flank downdraft's role remains confusing with respect to tornadogenesis. Truly confirming evidence about the various aspects of numerical simulations awaits better observations, despite the compelling similarities between simulations and real storms." So here you see someone taking much more of like the how plausibly kind of attitude toward what they observed in the simulation. But what's important, I think, is that when you, so we could think about, epistemically what's driving these differences in attitude toward the results of the simulation. But from a more practical point of view, I think the neat thing is that once something like this happens, it sort of directs you to undertake particular empirical studies that would be particularly telling, which you might not have otherwise known to undertake. In other words, you may see something in the simulation results, and maybe you are like Markowski here, and you say, well, I don't want to totally buy into that yet, but now you know where to look, or you may know where to look in a way that you didn't know before, in order to see whether things really are happening the way that the simulation is suggesting. So then just to go back to that notion of understanding, it's probably obvious, but just to bring it together at the end of each little section, I want to tie it back to those notions of understanding that I introduced before, where explanation is obviously a part of each of them. So anytime you have help with explanation, I'm assuming you have help with understanding. But if we're using simulations in the way that I was talking about here, certainly we may have hypotheses suggested to us about the structure and dynamics of the phenomena, so that's that descriptive knowledge that we might be seeking. And I'm using the language suggest, right? I'm not saying we look at the simulation and, aha, now we know once and for all this is how the storm really is. But at least we may have things suggested to us in a way that, as the Markowski quote suggested, we might not ever have thought of on our own without having looked inside the simulated storm. Also, obviously, it can suggest how possibly and how plausibly explanations. And then the punchline, right? These may have been out of reach for much longer. That's what I was just getting at. It may not be that if we sat in our armchair and thought really hard for a long time that we would have come up with some of the proposals that have been devised. And as I said a minute ago, I think really importantly, once we get that initial suggestion, that can direct our empirical investigation, focus it and direct it in ways that would not have otherwise occurred to us. And then, depending on what happens, those how plausibly and how possibly explanations may come to be accepted. And that has happened in a number of cases with aspects of these severe storm dynamics. So the empirical is still there. There's still clearly an important role, but the simulation is also directing and contributing in a way that's really important. All right, so let's move on to the second way in which I want to talk about the use of computers in advancing understanding here. And that's in testing hypotheses. And we're going to go back to that quote from Charney that I showed you right at the beginning and look at a little bit more of it. So I'm going to reread what he said, what I read before. "The radical alteration that is now taking place in meteorology is due not merely to the ability of the machine to solve the known equations with known initial and boundary conditions, but even more to its ability to serve as an inductive device." And then he tells us a little bit more about what he has in mind. He says, "The machine, the computer, by reducing the mathematical difficulties involved in carrying a physical argument to its logical conclusion, makes possible the making and testing of physical hypotheses in a field where controlled experiment is still visionary, say experimenting on the atmosphere, and physical model experiment difficult, that's say dishpan experiments in the lab. And so it permits a wider range of inductive methods. So he saw the computer as a tool that would help us, as he says, right, carry a physical argument to its logical conclusion in a way that we might not otherwise be able to do. And this was meant to be understood as part of a larger inductive practice. And what I really think he has in mind here is trying to understand things like extratropical cyclones, the really large low-pressure systems that we see regularly populating the mid-latitudes. Obviously people knew that those were there, and they had some idea about their evolution, but what initiated them? This was, for instance, something that was still definitely under discussion and debate in the 1950s here. So the physical hypotheses that Charney had in mind were hypotheses about salient large-scale features of the atmosphere. We see all this stuff going on, these very salient features. We don't really know what is causing them. Like, what sort of conditions, what confluence of factors leads to the production of an extratropical cyclone. And I want to note as well, and I'll give an example of this in a minute, very early on, the value of the computer for testing climate change hypotheses was also emphasized by Ed Lorenz, for instance, and I'll have a quote from him in a minute. So what I want to do in this portion of the talk is just, I'm not going to do this in a sort of historically truthful way, but I'm going to show you what I think of as some of the kinds of hypotheses that they had in mind, not physical hypotheses, but the form of the physical hypotheses that they might have in mind when saying things like, the computer is so useful because it allows us to test hypotheses. Some people have the reaction that how the computer can't test the hypothesis. It's not an empirical, you're not doing something empirical if you're running the simulation. And that's true, and I think the way to think about how the computer is helping here is that it's helping with what we often take to be the simple step, like you derive the prediction. Well, you don't always just derive the prediction in an unproblematic way, right? You have your theory, you derive the prediction, you check and see if it's borne out, that sort of practice. It's helping us with that, with the deriving of the prediction in the sense of implication, let me be clear, not in the sense of future-oriented prediction. So I'm going to talk about three types of hypotheses that I think are the kinds of hypotheses that are that might be tested with the help of the simulation and might be important for promoting this goal of understanding. So one is hypotheses about changes or intervention. So you might have a hypothesis that says something like, very schematically, right? If we changed X, this would result in Y. And maybe we'd have some story like, first this would happen, then that would happen, and ultimately Y would occur. And so one way you might try to get some traction in testing that hypothesis is by building a simulation model in which you think you have adequately represented the causal factors that you think are in play here, and then checking to see whether that order of events occurs in the simulation. Right? So if you make a simulation where you think you have adequately represented those factors and the intervention, the change that you're interested in, and you find, I don't see anything like that specified order of events that I hypothesized. It doesn't culminate in Y, like I thought, in the simulation. That could be seen as evidence against the hypothesis. Maybe my initial H was not on. On the other hand, if I do see that specified order of events culminating in Y, maybe I say, I have some evidence here in support of H. Now, I'm being very slippery here. On my slide, I say, this is evidence for H. And when I'm speaking, I'm saying, we might see it as evidence for H, or we might interpret it as evidence for H. I think there's a lot of hard work going on in this adequately represent phase, and I'm going to put up one of my flags in a minute to flag that. But hopefully you can see that if you did believe that you had adequately represented those factors, then this sort of practice could help to direct your thinking about H. So this is all very schematic, but I want to show you this quote from Ed Lorenz, which illustrates why this might be valuable. So he's going to be talking about climate change, the causes of climate change, and he's talking about evaporation in particular. So let me just read this for you. I apologize that it's small and long, but please bear with me. So Ed Lorenz, writing in 1970 in an article called Climate Change as a Mathematical Problem, he said, testing of hypotheses about climate change seems essential if the hypotheses are not simply to remain hypotheses forever. For example, one might argue convincingly that a decrease in evaporation from the ocean would bring about a decrease in surface salinity, which would inhibit vertical overturning in the ocean and thereby favor the formation of sea ice, which would in turn bring about increased reflection of solar radiation and thereby lower the atmospheric temperature. So he had this sort of causal chain of occurrences, and he says, you might argue convincingly that that's what would happen if you decreased evaporation from the ocean. He says, such reasoning could be completely sound, and yet not be particularly relevant to the problem of climatic change, that is, understanding why large changes in climate have occurred in the past, for instance, if the decrease in temperature arising from the decrease in evaporation should prove to be negligibly small. So you've got the direction right, but what if the magnitude is really small? Or if the decreased evaporation should simultaneously initiate a second chain of events, which would favor a rise in temperature. And this is certainly one of the concerns that people have in trying to think about interventions on the climate system, that you might actually initiate several causal chains that are partly counteracting each other. So, but what he goes on to say, and this is really the important part, he says, yet all the essential features of this reasoning can be incorporated into a mathematical model. And the step-by-step numerical integration of the equations will then constitute a system of bookkeeping for the ensuing temperature changes. So it's sort of helping us to see whether our hypothesis that were we to decrease evaporation from the ocean, we would down the road, down the way, see some lowering of temperature that is significant. We can see, at least in the way that he's proposing here, we might set up the computer to do the bookkeeping for us, to not only check whether we've got the direction right, but whether the magnitude is going to turn out to be significant. So it's, in other words, it's very easy to persuade yourself about things and to not keep track of all of the interactions that are occurring, even though you believe that those interactions are occurring. To actually keep them in the front of your mind as you're doing the reasoning is not very easy. So that's one kind of hypothesis. You might also want to test, say, hypotheses about sufficient factors. Like you might want to say, suppose you hypothesize that a particular set of causal factors, and these might be conditions or processes or forces, that they're sufficient for producing some phenomenon or feature P. You may not even know how it does it, but you might just say, I'm going to hypothesize that this is sufficient for producing that, so you don't have that story of the causal chain in between. But then if you, again, build the simulation that represents those specified factors, and again, crucially in an adequate way, then if you don't see anything like P in your simulation, you can say, well, maybe that's evidence against the sufficiency hypothesis. And if you do see P, then maybe you've got some evidence in favor of your sufficiency hypothesis. Now, there's no great feats of logic that I'm doing here or anything, but it's just that you may, as Lorenz was saying, you may have these hypotheses forever sitting on the shelf and not really sure how to move beyond them being just the hypotheses. This is at least a step toward an initial check to see whether your reasoning and your thinking is correct. It may not settle the score, and here's where my flag comes up, because as I said, to think about the sort of evidence and epistemology side of this here, a lot of work is being done by representing these things in an adequate way. So what exactly does it take for this to be evidence? What kind of evidence? I think that is worth talking about more. And certainly people have done a lot of work in the epistemology of simulation. I'm flagging it here just because I think there's more work. There's more room for discussion on this. And so this is just a very similar case. Suppose you have a hypothesis about a necessary factor. Maybe you have a set of causal factors and you say, this set is sufficient, but I think if I took out the first one, C1, this factor, I would no longer have a sufficient set. C1 is somehow necessary, given the rest of the factors. So again, you could do the same sort of thing, right? You run some simulations, you leave out that factor that you hypothesized to be necessary, and you look and see, does the phenomenon still occur or not? And just to give you a concrete example, since I've left this all in a very abstract, schematic kind of form, if you think about simulations of late 20th century warming, and think about the role of greenhouse gases there. So what you see in this chart, and it's sort of broken down by continent, if you look on the bottom here, this is for the globe as a whole, this is for land surface on the globe, and this is for the ocean. But the black line is labeled observation, so that's showing a sort of change in temperature over the course of the 20th century. The blue that you see here are results from simulations that don't include anthropogenic forcing factors, so no greenhouse gases, just changes in solar output and volcanoes. The pink are what you get if you include both the natural and the anthropogenic factors. So once you bring in the greenhouse gases and so on, the aerosols, then you end up with simulations that much more closely track the observations. So this is just sort of illustrating this idea that we might say, the set together is sufficient, the anthropogenic factors are necessary. Just a sort of concrete illustration, very simple illustration. but giving you the sense. And of course, there's this deep question. I mean, there's a lot more to say before we can then go on to say, so it therefore is greenhouse gases that caused it. But in the context of this set of factors and the way we've represented the processes in the model, it looks like they're necessary, right? All right, so to finish up this little section on understanding then, on testing hypotheses and understanding, right, the obvious connection here is with explanations. And this was from the start. When someone like Charney was saying, we can make and test physical producing it, that can prevent you from wasting time trying to find an explanation in terms of those factors. And lastly, right, learning that the factors are necessary can strongly constrain the space of explanations, in other words, the range of mechanism descriptions that you should take seriously if you're on the hunt for an explanation of the mechanism by which the phenomenon is produced. So what I'm trying to flag here is just this idea that being able to carry out the kinds of tests that I was just describing can be a sort of resource in the context of searching for and constructing explanations, which in turn is related to this goal of understanding. All right. And now for the last section that I want to talk about here, the last sort of way in which computers are being used to advance this goal of understanding in this particular field. This is actually related to the last section. It is about testing hypotheses, but it's a little more than that. So you might see some connections. But the general idea is this idea of being able to experiment on models. So not say you have a hypothesis and now you want to somehow test it, but that you're going to sort of manipulate and play with your model in various ways and see what happens in effect, right? So turning off certain physical processes or varying the values of parameters and looking to see how the results change in light of those adjustments. So you might ask, for instance, if I include more realistic topography in my climate model, does it make much difference to the amount of rainfall that I see over the US? Or does it not make much difference? This question about the effects of topography was really important and on the minds of people early on. How realistic, and still, how realistic does the topography have to be? And then what you learn in this way, what you learn about the model from these sorts of experimentation activities, can at least provide a starting point for developing accounts of the mechanisms by which the corresponding real-world phenomena are produced, and the effects that you would see if you were to carry out particular interventions. So it's a starting point. And now, you might be saying, well, sure, that's right, I think that's an important use of models. It was actually an approach that was recommended way back by Charney and Lorenz and people as the idea of simulating the atmosphere was even becoming a possibility. People were very explicitly advocating an approach to understanding that involved a kind of experimenting on models. So I want to go back briefly to this time when numerical weather prediction and simulation of the atmosphere was just being born around 1950. It was in the context of this project known as the Meteorology Project, which took place at Princeton's Institute for Advanced Study. It was actually overseen by von Neumann, who saw the nonlinear problem of weather as a great test case to which to apply the computer. Jules Charney, whose picture I've showed you a few times, he was sort of the guy spearheading the development of the model for purposes of this initial attempt at simulation. And it's true that weather prediction was part of their goal. It was going to be a great practical payoff, worth a lot of money, right, if you could forecast the weather more accurately. But as I said a minute ago, Charney really said, this is a chance for understanding, and we should approach this in a particular way. And he says this in various papers here and there. And so I'm going to show you my abstracted reconstruction of the kind of thing that he had in mind. The idea was you start with a very, very simplified model. Lorenz would call it the maximally simplified model of the dynamical equations. And then gradually, you make the model more and more complex by adding in causal factors that you think are important, or by making ones that you've already included more realistic. And every time you do that, every time you move in this stepwise, deliberate fashion, you observe how the behavior of the system, the model atmosphere, changes. So if I add friction, if I add a primitive hydrological cycle, how do things look different after I do that? And in this way, at least you begin to determine causal dependencies in the model. It's a starting point. And if you have faith in the equations that you've chosen and the way you've implemented them, you hope that it's actually telling you something about the real system as well. But it's at least a starting point. And then the idea was you use what you learned about the simple models, these gradually increasing in complexity models, as a way of, as a resource for interpreting not only your more complex models, but the real thing. So the idea that we had an opportunity here to do things in a particular way was explicitly discussed. And you find some lovely quotes from Ed Lorenz along the same lines a little bit later than Charney was writing. So in 1967, getting at this idea that we don't just want accurate simulation, we need these simplified models. He says, the total behavior of the atmospheric circulation is so complex that the relative importance of various physical features, such as the Earth's topography and the presence of water, is no more evident from an examination of numerical solutions than from direct observations of the real atmosphere. So he has another example where he says, suppose we had a perfect simulation of a hurricane, a perfect simulation. We could look at it and say, I still don't know why the hurricane does what it does. I have a perfect simulation of it. He says, it's only when we use systematically imperfect equations or systematically imperfect initial conditions that we can begin to gain further understanding of the phenomena which we observe. For if we omit the terms representing specified physical processes, such as friction, from the equations, or if we fail to include certain observable features, such as cloudiness, in the initial conditions, we may, by comparing the mathematical solutions with reality, gain some insight concerning the relative importance of the retained and omitted features. Right? So he too is seeing this idea that we need a sort of hierarchy of models of increasing complexity, and we try to leverage what we learn about the simpler models when it comes to interpreting the much more complex ones, which, frankly, when we look at them, we might as well be looking at the real atmosphere because we don't know what's going on. So what happened? I said this was the approach advocated early on. What happened to today? Well, if you read various publications today, you will find lots of people still saying it's very important to have a hierarchy of models. However, I don't think that the sort of careful, systematic approach ended up being pursued. It was too tempting to just build fancier and fancier models before figuring out how the simpler ones really worked. So as computing power increased, you were able to increase resolution, you were able to add more processes. If you want to improve your model, a lot of times the default assumptions will, let's put in some more processes that we think are relevant, right? Without understanding really how the ones we already have in there are doing what they're doing. And this was actually discussed in a very nice paper in 2005 by fluid dynamicist Isaac Held at Princeton in this paper called The Gap Between Simulation and Understanding in Climate Modeling, where he sort of laments this and gives a kind of call to arms, like we need to do better, we need to change our discipline to take this kind of approach seriously, not at the expense of pursuing complex models, but in a more sensible way so that we can use what we're learning in both contexts. So he makes this neat analogy that I want to share with you with molecular biology. And he says, boy, those molecular biologists are so lucky because they get a ready-made, evolutionarily connected hierarchy of model organisms. Nature gives them a hierarchy of models in the form of different organisms. And so he points out, right, that if you look at what goes on, researchers have spent a huge amount of time trying to understand things like Drosophila or E. coli, these very much simpler organisms, right? And he says, to the great, payoff for biology. He has a quote at one point where he says, imagine how much progress would have been made if they'd only been able to study the human, right? So he's thinking the molecular biologists are so lucky. We need to, be more like them in the climate case, but of course we don't have a ready-made natural hierarchy. We have to construct ours. We need to construct this set of mathematical models of increasing complexity, what he calls hierarchies of lasting value. So he raises this point that there might be ways of constructing hierarchies, multiple hierarchies, that where some might be more useful than others, and so opens this interesting question about what would it mean to design such hierarchies. So he actually talks about the E. coli of climate models and his own personal candidate for what should be the E. coli of climate models. And then it also mentions things like models of intermediate complexity that climate scientists take, quote, just as seriously as do the biologists who map out every single connection in the nervous system of the snail. You know, so sort of really trying to understand how the parts are doing what they do in this intermediate complexity model. And I just have one more quote from him and then I'm ready to conclude. He says, despite the extra burden of trying to create a consensus as to what the appropriate climate model hierarchies are, the construction of such hierarchies must, I believe, be a central goal of climate theory in the 21st century. There are no alternatives if we want to understand the climate system and our comprehensive climate models. So I'm going to put my last flag on there because I think this is a really interesting couple of questions here, really. What are hierarchies of lasting value? How would you think about the task of designing appropriate climate model hierarchies, which for him means these hierarchies of lasting value, so things that we will be able to glean insights from that are useful in the long run. And then the second aspect of the flag, is there really no alternative? I mean, that is an interesting question. Are there other ways of making progress in understanding the climate system that don't proceed in this way? And flagging it as a question for you to do more work on it. It's a very strong statement, right? There are no alternatives. But try to think to yourself, what would be the alternatives? What could there be in its place? So then, just to wrap up this third part then, this experimenting on models or exploring hierarchies, obviously you can see that would have some connection with explanation. The whole idea really, as I see it, is to build a kind of storehouse of information about dependencies in models and then try to leverage that storehouse as you're interpreting, you know, the ones that look like a blooming, buzzing confusion when you first look at them. And I'm going to say this, but I'm not too prepared to back it up very well. But I also think that this kind of experimentation and exploration can create a kind of familiarity with the behavior of the models, with the behavior of model atmospheres and model climate systems, that can help scientists develop that skill that I flagged as being an important part of understanding complex systems in the broader sense. So I think there's something about that experience of interacting with the model over time in lots of different sorts of nudges and changes and looking at how it responds that somehow I think facilitates the development of that kind of skill. So I'm going to make that claim, but as I said, I don't have a lot of evidence to back it up. It's just a conjecture, perhaps. Plausible, I think. So just to conclude then, what I've tried to suggest is in this field, in the study of weather and climate, prediction is important, but the computer has been absolutely indispensable, it seems to me, or it's just been tremendous as a resource for understanding, both in the sense of understanding why some phenomenon or event occurs, and in understanding in this broader complex systems kind of way. What I talked about were three ways that computer simulation in particular has been used to promote these kinds of understanding. The first, as you may recall, was by providing these surrogate observational data, which can suggest descriptive and explanatory hypotheses. Second, by facilitating the testing of explanatory hypotheses. And third, by allowing scientists to explore the behavior of simplified systems that can provide a starting point for interpreting more complex ones. So I'll just leave you with my flags of opportunities where I think, and these of course are just some, I'd be happy to hear other things that you think should be explored in connection here. So thank you very much.
So I will keep a queue of questions, but I want to take a moment to encourage everybody to take advantage of the coffee and snacks that arrive. So maybe we can take a brief moment and then we'll go to Q&A. Okay, so. So, is there only one of those? Okay. Okay, I think we're ready to get started with the question and answer. So I have a question here. So just try to catch my eye if you want me to put you on the queue. And there's a microphone that I'll bring around so that you can be heard by everyone. Our first question is from Bill Harper.
Thank you, Wendy. That's a great talk. Now, could you go to your slide about the downspouts, the circular storm and the downspouts that you had?
Let's see. Do you mean the rear flank downdraft?
Yeah, right. The rear, right.
Okay. Get in there. Did it seem that long? There, that one?
Yeah. Now, so you had, you told us about the models running, where they found that you had the rotational increase first, and then you would get the downdraft. And then you had somebody saying, look, this resolved it, and evidently a lot of people were convinced by that. Now, one of the things that would be really effective, it would be if you could run the models, run versions of the models, without having the rotational increase and see whether you still get the downdraft or whether, and run them in various ways. And now I know that the fluid dynamics stuff is a lot harder to do that sort of thing with than the sort of stuff I'd be more familiar with. But was that done? And what do you think? In my opinion, that would make a huge difference.
Sure, I think that the kind of rotation they're talking about is something that emerges over time as the storm is evolving. So it's not something where they could go in and in an easy fashion say it's not that there's a sort of parameter or set of parameters that could be tweaked to reflect that. It's something that emerges as the storm develops. So I think the answer is I don't think that they've been able to do something like what you're proposing. However, what they have explored is relatedly sort of the kinds of environmental conditions, for instance, how the wind shear changes with height, how that affects whether storms like this occur in the first place. So the kind of approach that in an abstract sense that I think you're describing, they sort of are, say, changing what the wind profile looks like, changing how much potential convective available potential energy there is, and seeing whether these kinds of rotating storms occur at all, the kind of supercell storm, because they are a somewhat rare beast. But in terms of actually manipulating that low-level rotation, it's just something that emerges as the storm unfolds, that they can't just turn off, as far as I know.
But now, could they run a lot of variations of models and see that it kept happening?
Right, so they could do that, and
have they done that?
They have. I don't know. The story soon becomes very complicated because it turns out that there's more than one kind of supercell. There are more than one kind of rear flank downdraft. So basically, things start with a kind of fairly simple conceptual model of what the storm is like, and then the more they do, the more they recognize there's the type 1 and the type 2 and the type 3. And depending on which one of these types it is, I think for some of the types it's not actually resolved yet. But these are the kinds of explorations that are done. So I can't speak to the details, but...
No, I did have another question about the hierarchy.
Okay, so go ahead, and then I have other people.
Okay. So the hierarchy is, of course, very dear to the heart of Newtonian methodologists, because that's exactly what happened with the application of Newton's theory to the solar system. But there were features about that made it a lot easier there. So Newton started by taking the basic Kepler orbit, and that's what you would get if the only force acting on a planet was inverse square attraction to the sun. And then gradually people, a little bit with Newton, but a lot with people following, where you take the basic model and then you look for deviations in the model. And then you would use those deviations. If you were successful in finding a perturbational interaction that would account for it, then you'd be seeing how the deviations are actually carrying information about this causal structure, and then you would form the next layer, and then you would continue, and it was that really was this awesome quality of evidence that George Smith has beautiful paper pointing out in the Stanford Archives that was there for. Now, one of the things that made it easier to do was that how to put it, the dependency of the higher order effects are small relative to the first order effects. And of course, in fluid dynamics, that's really not that's going to be a lot harder. But this idea of looking at simpler models and then adding complexity, and also paying attention to the order in which you do it, because it might make a big difference. Anyway, that seems like a very promising thing, and is analogous to the stuff that was so successful in gravity and cosmology.
I think that's really interesting. I think in a way, I think of the case you're describing as a little bit different in the sense that you're sort of uncovering, if I'm understanding correctly, right, you're sort of detecting the presence of other masses and detecting that other things are there. But it's a really interesting way of using something like a hierarchy. But here, the case, I think it's more like you have many, many causal factors that you already think are present and acting, and you just don't know what's doing what. And it's a way of...
But starting with a simple model.
Yes,
and
absolutely.
then looking and then seeing.
Yes, absolutely. Thank you.
Thank you very much for your talk. I enjoyed it a great deal. I'm interested to ask, so you presented several things that you think that the computer can be used to kind of help us beyond mere prediction. I'm curious whether you think that the list of things you've offered is exhaustive, or whether there are other things, and if so,
my short answer is I doubt it's exhaustive, but I don't have any other ones in my back pocket that I really wanted to tell you about, but didn't. Did you have something in mind yourself for something you thought was?
I imagine there's a great kind of heuristic in having these models, perhaps to highlight various features of complex phenomena that might kind of come out with very simple models. Now, that's not to make use of for the purposes of hypothesis testing or for anything else, but nonetheless, it serves an important function, say, for the training of atmospheric science.
Okay. So a kind of pedagogical,
right?
Which may have actually, what's used in those pedagogical cases may actually have been something that came from some of these cases where people were trying to develop a hierarchy for sort of basic research understanding, but then you come to recognize the value of the model for making certain kinds of points for students as well.
Right.
Yeah. I would also add, if we don't limit ourselves to simulation, we could probably talk about the use of the computer in all sorts of data analysis and other visualization. All of those things are really important, but I first interpreted your question just to be in the context of simulation and so on. So. Just getting back to the end here.
Hi.
Hi.
I just got a question. It's a follow-up on your answer to the first question. You kind of made it seem like a throwaway remark that you mentioned it turns out that there are different types of supercells, and it turns out that there's different types of this down here plane and down route. Is that something that we learned from these computer models? Is that an insight that was an understanding that was created through this computer modeling? Or is that an example of it, or is that something that is different? And has that been tested since?
So I actually don't know the answer to that, but I think that a lot of that came from observational studies and getting some better data. I'm not prepared to talk about all the details of the different types, but like some of them have, say, the temperature is different in the region near the downdraft, and so there are some like thermodynamic properties that are different in some of these different types, and I think there's just a lot of questions still unanswered about those. But to my knowledge, those were not types that were distinguished via simulation. I think they were the types that were distinguished via more traditional observational investigations, but I really don't know for sure. But I could direct you to a few papers where you could check on it. I'm sorry, I can't say it.
Thank you very much for that. It's very interesting. I was hoping you could say a bit more about the relationship between prediction and understanding, because it seems to me that in a lot of the philosophy of science literature, these often go hand in hand, whereas you've kind of taken them apart and you want to talk about them individually. And I'm wondering if you see possibly one preceding the other as either coming first, or perhaps as being more important, or if you see them actually as being part of the same project, just doing the same thing, just under different names, in a sense.
I guess I do see them as different. So I don't see them as doing the same things under different names, though I can certainly hypothesize about the kinds of views of the relationship between explanation and prediction that you might have in mind, a sort of symmetry thesis or something like that. The reason I think that they're different is not different, universally and categorically. So I think it depends on the practice and on the context. But I think that it can very easily be the case that you are interested in prediction in a way where you're happy to make certain kinds of fudge factors that you don't understand but that seem to work. And you're really not concerned about unpacking why they work, as long as they work within the bounds of the project that you're interested in. That's okay. And I feel like there's a kind of divergence there in the attitudes toward, whereas if I'm thinking about understanding, I'm thinking that, I want to understand the system. I don't want there to be these kind of black box placeholders that are doing a task for me that I'm satisfied with, but I don't really know why exactly they work or what they're replacing in a satisfactory way. So I think that those two goals speak differently to model construction, model evaluation, and the kinds of things that you're going to be satisfied with. I don't think it's black and white, right? Because obviously, if I'm interested in understanding a certain kind of phenomenon, I might be fine with black boxing some other things in my model that I don't think are particularly important to understanding the thing I'm focusing on. So it's not a neatly separable thing, but I don't see them as tightly linked in the way that.
Do you see, in that case, understanding entailing accurate prediction?
Not necessarily. No, I think it depends on the kind of system. For some systems, what you need to do accurate prediction is just, for instance, think about weather, right? We might understand the atmosphere quite well in many respects. We might, hypothetically, in the future, even if we don't now, we might understand it, and we still might not be able to predict because of chaos, right? Because of the chaotic nature. If the atmosphere is chaotic, we may never get our initial conditions to be accurate enough to have the kind of long-term prediction we want. So they're not unrelated, but they're not attached constantly. Yeah.
Thanks, Wendy. Right at the beginning, you talked about how in the 50s, one of the inspirations for doing this kind of work was they couldn't solve the equations analytically, right? It was just too hard to do at that point. And then it sounds like they got simulations and they were able to, by numerical methods, make better predictions, right? But one of the criticisms of numerical methods in applied mathematics is you can get good predictions without necessarily getting good understanding of what's going on, right? So I'm wondering, and this is tied into the point you were making later in the talk, right? Following up on this theme of understanding and explanation, you get good prediction without necessarily getting a good understanding of what's going on and what the causal factors are. So I'm wondering whether there has been any progress in analytic solutions to those equations, or whether it's just still way too hard.
As far as I know, nobody's trying to tackle the problem of weather prediction via analytic. So you can solve maybe for some certain kinds of idealized cases, but not the kind of, initial and boundary conditions that are relevant for the weather. So I don't think so.
Maybe here's another way of thinking about it. Thinking about the hierarchies of toy models.
Yes. Mm-hmm.
could that be a way of figuring out where, if there are certain cases that are analytically tractable now, could those be toy models that you could start with?
Sure. Yes, I think that is true. So you might have a very simple energy balance type model where you might be able to do some calculations. So, for instance, in the 19th century, when people were worrying a little bit about increasing carbon dioxide, right? Initial calculations for how much the atmosphere would warm were sort of done with paper and pencil, some approximations. Maybe they weren't analytics. Maybe that's not a good example. But I think the answer is yes. But what I really want to ask you in reply is, why do you think that would be important? So why?
So
suppose if there were some analytic solutions, why would that be important?
So this is, I guess, I'm thinking about physics cases, right? And taking toy models where you can try and get analytic solutions can give you some insight into what's going on. But in this case, it's not clear to me that the sort of causal factors that you're interested in, because you were thinking of the hierarchy in a more causal kind of way and adding more causal complexity.
Yes.
It's not clear to me that what's analytically solvable is going to track.
Exactly.
Right.
I think that's right. I think the kinds of cases for which you can do analytic solutions are going to be different from the kinds of cases where you have the causal factors that you're interested in untangling represented. So,
okay.
Yeah. I wish it weren't so, but.
Thank you, Wendy. That was a wonderful topic. We're reading about mechanistic explanation last week. I said you just turned to just talked about.
Could you speak up a little bit?
Yeah, sure. We talked about how possibly and how actually and how possibly. And my question was, in terms of these models moving from more simple to more complex and introducing factors in the mechanistic framework, you have decomposition and localization.
Right.
And is this the correlate? I mean, that you could never have a mechanistic explanation if you didn't have, in this domain, if you didn't have that kind of approach. I mean, is that what is kind of being, would you say that is what's kind of being argued for?
I think so. I tend to think of it along those lines, the decomposition and localization, not in those terms, but that's. I don't think there's as much the localization. Well, maybe you could still talk about localization. There's not talk about function in the same way.
Right.
But there's still talk about, the causal processes that are responsible for certain phenomena. It may not be their function to produce those phenomena, but I do think that it's analogous. And I wouldn't rule out, I do think that there are some people who are very, very smart who have an idea of looking at the atmosphere in just a really different way, I'm not even sure I understand at this point to say much about it, but from a sort of thermodynamic perspective, that's just very different from the kind of approach that's being taken here. And so I would leave room for there being some other way of approaching it, but I would say in the traditional way in which this study of the atmosphere and climate system have been approached, it is very analogous to that, and it's about untangling the causal contributions of lots of different factors that you pick out as causal factors.
Right. No, and why I thought it was interesting was, in terms of moving from animal models to the human case in neuroscience, my thought is you have to increase complexity by virtue of adding, changing your stimulus parameters, for example. And so it's there are a lot of parallels. It makes me think that volume should be written just
I think that it is actually a lot of the times when I'm thinking about this, I do come back to, say, Bill Bechtel's work or Bill Limsat's work, and people who have been thinking about complex systems and often complex biological systems, and I see them as very similar kinds of activities, even though the subject matter is very
great.
Yeah.
I'm going to use my position as chairman. Sorry. I'm really curious about what kind of assumptions go into this picture of a hierarchy and causal factors and all that, because there's a really natural worry that for nonlinear systems you won't have a straightforward composition of causes. So when you have independent models of separate causal factors, they might work fine in that model, but you add them in and you have a nonlinear system of equations and suddenly things look very different. So there must be some assumptions that underlie the idea that you can have this sort of hierarchy, or so that the bits of the hierarchy play together well as you add them together.
Yeah, that's a really great question, and I think that the assumption is that hopefully it will work some fraction of the time, because we don't know what else to do. But you're absolutely right. And whenever I start thinking about that, the way I comfort myself is by saying, well, it's an empirical question, right? How much is it like that? How much do things work additively for our decomposition of the system? To what extent can they be treated in that way, to within the bounds that we care about? So absolutely good question. I don't know that I have seen people say having explicit arguments about why, say, additivity would be appropriate here. I've seen that in other contexts when people are arguing about, say, the causes of climate change. A lot of the methods assume a kind of additivity, and there has actually been a lot of work there to probe how reasonable that additivity assumption is. But in the context of this our sort of philosophy of approaching this, the hierarchy approach, I think it's kind of like, well, do you have a better idea? It may not pay off, but at least we have a starting point for, as long as we're cautious and careful, at least we can get the game going.
Sorry. I'm not sure. Maybe another version of the same thing. Yeah. It is another version of the same thing, and I'm struggling to articulate it. So when I think about the Drosophila parallel, one of the things that I worry about is that I think, Drosophila have been wonderful, and they've revealed a tremendous amount, but they've also been really misleading because they're really strange. And one of the ways in which they're strange is that they allow the separation of some causal factors that in lots of organisms are not well separated. And there at least was a stage, and arguably we're still in it, in which our biologists' broad understanding of organisms, and especially of heredity and of evolution, was really distorted by the fact that what we really knew about was not organisms, but was fruit flies. And it's possible to say, then, that's okay. It's an empirical question, and it gets sorted out in the long run. And people are now starting to notice that, for example, plants are very, very unlike Drosophila in ways that matter. And indeed, mammals and indeed humans are very unlike Drosophila in ways that matter, right? And sort of in that case, it seems perhaps as though that was okay. That was a stage of a developmental stage that we had to go through that then gets us. Gives us a certain kind of understanding that then we can develop as we go along. But in the case of climate science, it looks like we don't have time for that. And also we don't have the kind of data that would help us out, right? The only way that the correctives can come along is by our projections being wrong. And we sort of don't have the luxury, right, of making the oversimplified projections. And the place that I see it is, I notice something that I kind of notice in the climate reporting news is it seems quite frequently that we hear about a feedback effect, a positive feedback in climate change, turning out to be very important. And what the reporters say is, and this isn't even in the models. And often these are feedbacks that, in retrospect, it seems could have been first seen right. Basically, people have been talking about them informally at least for a long time. So one of the things about this, the climate side of the climate and weather here, is that if you want to tell a story about that allows for this sort of separation between understanding and prediction. In lots of contexts, that seems fine, but in specifically the case not of weather, but of the science of climate change right now, it seems as though prediction has assumed a kind of special importance that it just doesn't have anywhere else, and understanding without the capacity to predict over the next 100 years is not good enough, right? We need prediction. So that just makes me wonder about whether this. The first response that one ought to give in your position is, do you have a better suggestion? Obviously. But there is something to be said for not following the path of the Drosophila scientists and spending a long time being kind of mesmerized by our simple picture and thinking that that gives us what we need, when what we need is to be taking adequate account already of the feedbacks that we sort of know are there. And so it's not really a question, but please comment.
Okay. So I think you do point out something that I should emphasize. I do think that a lot of this talk of understanding and hierarchies from Charney to Held all the way, it's not coming from a place that's motivated by we have to solve a practical climate problem. It's coming from a basic science. We want to understand the system, and this is part of the process. But you raised the point that, well, we're also in a special situation here where if we can have them, we would like to have good predictions. And to the point to your point related to why aren't some of these processes already in the model, I mean, model development is a long process itself, and sort of the speed of science there is itself moving very rapidly by its own standards, but that doesn't mean that we can represent tomorrow all the things that we think are relevant today. So there is a general speed of science problem that is relevant here given the concerns about climate change. And then there's a whole other discussion we can have about whether we really do need predictions. So I'm not going to go into that.
Mine is a follow-up question, Sir Chris. It's true you have the nonlinearities here, but it's also true that if you're talking about a model and then going through the process of putting in the pieces to start with, the nonlinearities are going to show up in the way it goes anyway. And it's an empirical thing of how much you would, of just seeing how going through the steps, what differences they make. And by the way, it brings up an important reason for the order in which you do it, because those might make a difference where they wouldn't make a difference in the case I like, in a linear case. But it still doesn't follow from the fact that you can't. It also notice you got the one. You take one of the best complex models, and then do what he said about taking it apart and doing piece by piece and just see. And look, with the computer, you can do it all different ways and just see what difference it makes. This is a kind of empirical question. I mean, and one of the things that the computer is really good, a fine resource to help you do that with. So I think that even though the nonlinearities are there, they needn't be something that would completely undercut the capacity of this sort of thing to be illuminated.
Yeah, I think that, but there's the question of whether what you learn at one level in the hierarchy, how much does it transfer to the next
Well, this is why you need to run through it, and why the different orders different. And notice, in this, we're not talking about, like in the solar system, okay, we got this far and then we keep working. But in this case, the research, right, look, you got the big model, and then you can run this different ways and do it. And then that might give you ideas for even more improved things. But so it doesn't have to be sticking with a partial model and taking that as your whole story. You're not doing that.
Absolutely, absolutely right, yes.
Sorry, we have one more question, I think. Time for one more.
Thanks, Wendy. I had a similar question to Rebecca's, so I'm wondering if I can push you a bit more to explain this explanation-prediction relation.
Great, because it's still kind of bothering me in the back of my mind, so I'm glad that you brought it back up. Please proceed.
So I think I get the idea that you can have prediction without explanation in the case of these black box models where you get some output that allows you to make a prediction, but you don't know exactly why. But I'm wondering if you can say the same about explanation. You have these models facilitate some sort of explanation about a system without it being able to predict what is happening with the system. So with the examples that you have from the IPCC that help us explain the forcing mechanisms of climate change and our role in climate change. These are thought to be reliable in part because of how well we can sort of retrofit the past climates. So can you have any kind of explanation without that sort of predictive element?
I think you can have models serving in a sort of heuristic role where they're sort of serving as inspirations for proposed explanations, even if they maybe don't give good predictions at all. But I do think that, I think it's more a question of, or I guess I'm inclined to say something like, the fact that you can explain suggests that probably you can predict some things. It's just a question of how much can you predict and what are the limits of that prediction. So could you have, what I was trying to explore was whether I could imagine a model that really, for all the kinds of predictive tasks we cared about, didn't do much for us at all, but was still somehow explanatorily useful. And I thought, well, maybe I could imagine it being a sort of spark for my thinking or something, in the way that it deviates from the real thing. But if I can't explain, if I have a model that I take to facilitate, like if I can tell a causal story, say, using my model, I would assume that what goes along with that is an ability to predict certain things. Some things should be predictable then, but the question is just how much. Maybe that's more satisfying. Is that addressing your question? Yeah? Okay.
Okay, well, to thank Wendy, I have a prized philosophy department
Awesome.
mug.
Thank you.
A tote bag
Thank you very much.
to take with you to Durham, and let's thank Wendy for a great talk.
Thank you.